Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the previous lecture, we studied modal analysis of multi-degree of freedom systems with proportional viscous damping. Many systems in practice cannot be approximated by proportional viscous damping model. In this lecture, therefore, we are going to talk about modal analysis of multi-degree of freedom systems with non-proportional viscous damping. So, we are going to talk about modal analysis of multi-degree of freedom systems with non-proportional viscous damping. So, a brief outline of the lecture is as follows. We will first define eigenvalue problem and then see what are the nature of the eigenvalues and eigenvectors. We will define then orthogonality properties, look at how the normalization of mode shifts or the eigenvectors can be carried out. Then we will define the free vibration solution, also look at the model, and then we will look at the force vibration response of the system when harmonic forces act on the system, and then at the end we will define the frequency response function matrix and its relationship with the model. So, let us start with first of all definition of eigenvalue problem. So, the equations of motion for a system with non-proportional viscous damping would be mx double dot plus cx dot plus kx is equal to 0, right. So, this is nothing but the equation of motion for the free vibration, and if we assume the free vibration solution to be of this form, that is x is equal to x naught e to the power st, and if we substitute it in the equation of motion, what we get is m s square m plus s c plus k, right, into x naught e to the power st is equal to 0. So, since e to the power st cannot be 0 for a arbitrary t, what should be true is that s square m plus s c plus k x naught should be equal to 0. So, this is again the quadratic eigenvalue problem, same as the one we got for the case of proportional viscous damping system, right. So, now in this case, in the case of proportional viscous damping system, we use a modal approach to solve this problem, and we utilize the eigenvectors of the corresponding undamped model to define the eigenvalues and eigenvectors. But that approach we cannot adopt in the case of system with non-proportional viscous damping, because the eigenvectors of the undamped model, the corresponding undamped model, will not be able to diagonalize the damping matrix, because the damping matrix is non-proportional, okay. And hence here we are going to follow an alternative approach where we transform the equations of motion into state space and then define the eigenvalue problem in state space, right. So, therefore, this instead of this quadratic eigenvalue problem, we are going to transform the equations into state space and define eigenvalue problem in state space. So, let us go to next page. So, let us try to obtain equations of motion in state space. So, the equation of motion in terms of the displacement vector x, right, there are n number of differential equations, simultaneous differential equations, and each equation is of second order. So, we require around 2n number of coordinates variables to define the state of the system. So, we choose let us say the displacement as the first n coordinates. So, x, right. So, this is of size n by 1. So, let us say ZD, vector ZD represents the displacement coordinates, the n number of displacement coordinates, and then we take the n number of velocity coordinates. The velocities at all degrees of freedom, they are the, let us say, second set of n number of state variables. Okay. So, this is the choice of state variables. So, these are nothing but state variables. Now, if we differentiate these equations with respect to time, we get z d dot is equal to x dot and z v dot is equal to x double dot. The equation of motion we have got is mx double dot plus cx dot plus kx is equal to 0. So, now we replace these vectors in this equation using the state variables. Okay. So, in place of x double dot I can write down zv dot, in place of x dot I can write zd dot, right, and then in place of k, in place of x I can write down zd. So, that is one equation we got, right. So, this equation is now in terms of the state variables zd and zv and their derivatives. We can also write down zd dot, okay, as which is already equal to x dot. This we can write equal to zv, right. So, zd dot is nothing but zv, right, and if we re-multiply this equation by mass matrix, then the equation we get is minus m zv is equal to 0, right. So, therefore, if we call this as equation number 1 and this as equation number 2, then now we can combine these two equations and by into a common single matrix equation. So, let us define state vector, which is vector z, as a vector whose first part is the vector zd and whose second part is vector zv. So, if we combine zd and zv into a single vector, we get a state vector of dimension 2n by 1, right, because each of these vectors zd and zv, they are of dimensions n by 1. So, therefore, let us try to write down these two equations, combine them into a single matrix equation like this. So, z d dot and z v dot. So, this would be C matrix, then we have M matrix here, and then plus we have z d and z v is equal to 0. So, from the first equation we will have k here and 0 here, matrix of zeros, and then here from the second equation I have m here and 0 here, matrix of zeros, and here I have matrix of zeros, and here I have matrix M, right. So, therefore, we can see this equation number 3 is equivalent to equation number 1 and 2 because it has been obtained by combining those two equations. And let us represent this coefficient matrix as matrix A, and this is nothing but state vector Z dot, and this is nothing but, let us call it this as matrix B, and let us call this, and this is nothing but vector Z. So, we see that basically we can represent equation 3 by symbolically in the form of equation 4, right, and each of the matrices in this. So, this is a state vector of size 2n by 1, okay. This again is a B is a matrix of size 2n by 2n, A is a matrix of size 2n by 2n, and Z dot is a vector of size 2n by 1, right. So, effectively this equation number 4 is a set of simultaneous first order differential equations, and there are such 2n number of equations, okay. So, this is 2n number of first order differential equations, correct. So, this equation number 4 is equivalent to the original equation of motion we had mx double dot plus cx dot plus kx equal to 0. The difference is that the original equation was basically a set of n number of second order differential equations, while the one we have got in state space, they are the set of 2n number of first order differential equations, and both are mathematically equivalent, right. So, it is an equivalent representation of the system in second order of in the space of the coordinate x. So, now we did, let us assume, let us go to next page, let us rewrite that equation A z dot plus B z is equal to 0. Let us assume a solution, let z is equal to psi bar e to the power st. So, here we are saying, let us say there is a coefficient vector psi bar which is an unknown vector, unknown maybe eigenvector, and s is the eigenvalue. So, let us say this is the solution, a free vibration solution, and if it is a free vibration solution, it must satisfy the state equation, right. So, by the way, this is the called state equation. So, it defines the equation of motion in state space, it is nothing but the equation of motion in state space. And for free vibration, right. So, if you substitute this, what we get? We get A S plus B into bracket psi bar e to the power st is equal to 0. Now, again e to the power st cannot be 0 for an arbitrary t, it is not 0 for arbitrary t, and hence if we simplify, so of course then we will have A plus B psi should be equal to 0, which also can be written as B psi bar is equal to S minus A psi bar, right. So, now we see that this is similar to the generalized eigenvalue problem we got earlier, right. It is in the format of the eigenvalue problem. So, this is the eigenvalue problem. It is an eigenvalue problem in matrices minus A and B. So, when this eigenvalue problem is solved, then we are going to get 2n number of eigenvalues, right, and let us represent them by S1, S2, Sn S n plus 1, S n plus 2 going up to S 2 n. So, these are the eigenvalues we will have, right, and we have the corresponding eigenvectors, 2n eigenvectors, and let us represent them by psi 1, psi bar 2 going up to psi bar n, then psi bar n plus 1 and going up to psi bar 2n, right, 2n eigenvectors. Now, these eigenvalues and eigenvectors, they have a specific structure, they have some specific properties or relationship. Let us look at the nature of these eigenvalues and eigenvector, right. So, nature of eigenvalues and eigenvectors. So, first thing we see is that when we solve the eigenvalue problem, the eigenvalues which result, they are complex conjugate, right. So, we get complex conjugate eigenvalues, right. So, if there are 2n eigenvalues, basically it consists of n pairs of complex conjugate eigenvalues. So, we have n pairs of complex conjugate eigenvalues, which basically means that if I take as any eigenvalue S1, then there will be a corresponding eigenvalue S1 star. For eigenvalue S2, there will be a corresponding eigenvalue S2 star, and for SR there will be a corresponding eigenvalue SR star, and hence the complex conjugate eigenvalues we can list as S1, S2 going up to Sn, and then the next set of n eigenvalues are complex conjugate of these first n eigenvalues, and therefore we can write them as S1 star, S2 star going up to Sn star, and the corresponding eigenvectors are also complex conjugate, right. So, we also have complex conjugate eigenvectors, right, and hence we have psi bar 1, then we have psi bar 2 going up to psi bar n, and then the next set of eigenvectors are complex conjugate eigenvectors. So, psi bar 1 and we put a star over it indicating complex conjugate operation. Then we have psi bar 2 star going up to psi bar n star, right. Another characteristics these eigenvectors have is that if we partition the eigenvector, right, then the second part of the eigenvector, the corresponding to the velocity coordinates, is found to be related to the first part of the eigenvector, which is corresponding to the displacement coordinates. In order to see that relationship, let us take the motion in say one of these pairs of eigenvalues and eigenvectors, right. So, if I consider, let us say, rth eigenvector and a corresponding rth eigenvalue corresponding eigenvalue, then the z can be written as vector psi bar r e srt, and if we partition this z into displacement and velocity coordinates, then we can write this as psi bar r e to the power, and similarly we can partition the eigenvector also into displacement and velocity coordinates. So, we can write this in this manner, right, and therefore, what we have got is that ZD is equal to psi d e to the power SRT, right, and ZV is equal to psi bar V e to the power SRT, right. And if we let us say differentiate this equation with respect to time, what we get is ZD dot is equal to SR psi bar D e to the power SRT, right. And if we compare these two equations, what is the result? Because we know that the left hand side of these two equations are equal, because ZV is nothing but ZD dot, right, and hence we can see that psi bar V vector is equal to SR into psi bar D, right. So, this is the relationship you can see we get, that the velocity part of the eigenvector is equal to the eigenvalue SR times the displacement part of the eigenvector, right. So, let us represent, this basically tells us that the two parts of the eigenvector are related, and to simplify the notation, right, let us simplify the notation. Let us simplify the notation by assuming that, or by denoting psi bar D by psi alone, right. So, if you use this notation, then we can easily see that the psi bar V will be simply equal to SR times, sorry, let me put subscript R here, R, right, psi bar R, this eigenvector, therefore, I can write as psi R and psi SR into psi R. So, this is what something which can be done, right. We can represent rth eigenvector in this manner. So, let us define now the eigenvector matrix. Eigenvector matrix is a matrix of 2n eigenvectors at 2n DOFs, and this each column of this matrix is an eigenvector, say phi bar 1, psi bar 2, then psi bar n, then we have psi bar 1. Now, this is the complex conjugate of the first eigenvector, and then this goes up to psi bar n, this, right. Then partition into two parts, and we write this as psi 1, and then this is psi 1 S1, right. The next one we write as psi 2 and psi 2 S2, right. So, this goes up to psi n, psi n Sn, and then this complex conjugate can be similarly written as psi 1 complex conjugate and psi 1, right, in complex conjugate into now complex conjugate eigenvalue, right. So, in this manner it goes up to psi n complex conjugate psi n complex conjugate multiplied by S n complex conjugate, right. So, therefore, this matrix can be now written as a matrix of say eigenvectors psi which is of order n by n, right, and then here we have the matrix psi star, and then here we have psi times a diagonal matrix of eigenvalues, and here we have psi star multiplied by a diagonal matrix of complex conjugate eigenvalues, like this. So, therefore, if you look at the order of these matrices, this is matrix of order n by n, this is n by n, all these matrices are in fact of order n by n. And this makes up the complete 2n by 2n eigenvector matrix. So, this is basically the structure of the eigenvector matrix. And also in this case the matrix of eigenvalues is SR matrix is a diagonal matrix of S1, S2 going up to Sn with non-diagonal element 0. It is a odd matrix of size n by m. And similarly, we have the matrix of complex conjugate eigenvalues, which is S1, S2, S1 star, S2 star and Sn star with non-diagonal elements being 0. So, in this way we have defined these eigenvalue matrices and eigenvector matrices. So, if let us go to next page, let us see what is the free vibration solution. So, in case of we saw in case of single degree of freedom system, we had two complex conjugate eigenvalues, right, defining one real mode. So, for this system also multi degree of n degree of freedom system with non-proportional viscous damping, we have now 2n eigenvalues which are complex conjugate. So, there are n pairs of complex conjugate eigenvalues and one pair of complex conjugate eigenvalues and eigenvectors, they together define one real mode of vibration, right, and therefore, the vibration in one mode, the response in one mode, okay, it can be written as Z, right. Let us say in one of the modes, let us say using the rth complex conjugate pair, if we write down, then that response would be psi bar r, right, e to the power SRT, right, plus psi bar r star. This is a complex conjugate eigenvector and complex conjugate eigenvalue, right. So, and then we have the coefficients here, say let us call it AR. So, this AR is the coefficient. So, that is an arbitrary constant. So, if you have all the modes participating, which is going to be the general case, right, because of the arbitrary initial conditions, then a linear combination of the solution in all the modes would give us the basically free vibration solution. Let us see now what are the orthogonality properties. Right. So, let us consider for the pth eigenvalue pair, for the pth eigenvalue eigenvector, we can write down we had the eigenvalue problem as B psi p, right, is equal to minus S p, then A psi bar p, right. So, that is the statement of eigenvalue problem in terms of the pth eigenvalue eigenvector pair. Similarly, for the qth eigenvalue eigenvector, we can similarly write down b psi bar q is equal to minus sq a psi bar q, right. Let us now pre-multiply this by psi bar q transpose, right, and also take the transpose, right, and also take the transpose of the resulting equation. So, what is the result of that? So, we can write down that here, that would be psi bar p transpose, and matrix B is symmetric. So, B transpose is B, and then we have psi bar q, right. This will be equal to minus SP psi bar p transpose multiplied by A psi bar q, okay. That is going to be the result of that. Similarly, this equation when pre-multiplied by psi bar p transpose gives us psi bar p transpose B psi bar q is equal to minus SQ psi bar q transpose A and psi bar q. Sorry, here this should be P, right. Okay. So, that is the result. So, now if we call this equation as equation 4 and this or maybe equation 5, because 5 4 we already used there earlier, and let us call this as 6, and now if we subtract these two equations, what is the result? If we subtract 4 and 5, what we get is SP minus SQ psi bar P transpose A psi bar Q is equal to 0, right, because the left hand sides of both these two equations are identical. So, they cancel out and we are left with this equation. And if the eigenvalues are distinct, right, then for P not equal to Q, SP will not be equal to XQ, and therefore, we must have psi bar P transpose A psi bar Q should be equal to 0, right. So, it means if we have two distinct eigenvectors P and Q, then they satisfy this equality, that is psi bar P transpose A psi bar Q is equal to 0. So, it means with respect to matrix A, the eigenvector P and the eigenvector Q, they are orthogonal, right, that is what it means. So, that is eigenvectors P and Q are orthogonal with respect to matrix A, right. And if you substitute this result in, let us say, equation number 4, equation number 5, then we also get the other property which says that psi bar P transpose is also into B, and psi bar Q I think I need to write down the subscript outside. I think here also I have done that error. Let me correct that. So, psi bar P Q P Q outside is equal to 0, right. So, it means eigenvectors are also eigenvectors P and Q are orthogonal with respect to matrix B also, is not it. So, these are basically the orthogonal properties, and remember these properties are in the state space, they are defined in the state space. The eigenvectors are orthogonal with respect to matrices A and B, not with respect to individual matrices of the system, which are the mass matrix, stiffness matrix or damping matrix, okay. So, this property is with respect to the state matrices, state space matrices. So, if we take P is equal to Q, let us say equal to R, right. So, if I take P and Q as the they are the same modes, and if that is R, then we can say that psi bar R transpose A, right, is going to give us psi bar R is equal to, it will be not equal to 0 and it will result into some number AR, and similarly psi bar R transpose B is going to give another constant BR, right. And is there a relationship between AR and BR? That we can work out by substituting, right. If you look at the rth eigenvalue and eigenvector, right. Okay. If you look at that, then from the eigenvalue problem we have the result that VB rth eigenvector is equal to minus SR into A and psi bar R, and if we pre-multiply by psi bar R transpose, then what happens? Then on the left hand side, because of the orthogonality property, this quantity would be simply BR is equal to minus SR, and the right hand side we would have AR, right, and therefore we see that SR is nothing but minus BR upon AR. So, the ratio of minus BR and AR is equal to the Rth eigenvalue. So, that is nothing but the relationship between AR and BR. So, let us see that how can we normalize these modes, right, these eigenvectors. Okay. So, currently the eigenvector psi bar R, it is scaled arbitrarily, there is no unit scaling, right. So, let us see how we can normalize that. So, normalization of eigenvectors. Okay. So, we would like to normalize the vectors such that the value of AR becomes 1, right, similar to mass normalization we studied earlier. So, let us say the normalized vector is say phi bar R. Okay. So, whenever we put bar over the eigenvector, it represents the eigenvector in state space. Okay. So, phi bar R is the rth eigenvector in state space after normalization, and if this is the vector, then what we would like? We would like that phi bar R transpose matrix A phi bar R should be equal to 1, that is what we want, right. So, in order to obtain this, what we do is that we define phi bar as psi bar R divided by square root of AR, right. So, when this kind of normalization is done, then indeed the value of AR would become 1, right, based on the eigenvector phi bar R. Okay. And therefore, the if you look at the normalized eigenvector matrix, So, if you look at the normalized eigenvector matrix, means eigenvector matrix based on normalized eigenvectors. So, each column of the eigenvector matrix is a normalized eigenvector. Okay. So, this eigenvector matrix phi bar would be equal to matrix phi, right. So, similar to the partitioning we did earlier, we studied the properties of the eigenvector matrix and we found that we can divide the eigenvector matrix into two parts. One is corresponding to displacement coordinate, other is corresponding to the velocity coordinate, and the velocity coordinates are of the eigenvectors are related to the displacement coordinates by this relationship SR. And then the second set of n eigenvectors, they are complex conjugate of the first n eigenvectors, therefore, these are phi star n, and the velocity part of these eigenvectors corresponding to the velocity coordinate part of the eigenvector would be the complex conjugate multiplied by the complex conjugate eigenvalues. Okay. So, this is nothing but the normalized eigenvector matrix, and then if you write down the orthogonality properties in for all the eigenvectors based on normalized eigenvector matrix, then we can combine all the orthogonality properties and then write a single matrix equation based on that. So, you can say phi bar transpose matrix A phi bar, this is going to be now a unity matrix, right, and phi bar transpose B phi bar is equal to, this is now going to be a matrix of eigenvalues S bar R, right, because we have seen earlier that the minus B R upon A R is equal to S R. So, this is going to be minus, rather this is going to be, let me just add a minus here, it is going to be have a minus sign, minus S R bar, and here what is S R bar? S R bar is the matrix of eigenvalues in state space, which consists of two parts. One is the part S R and other is the part S R star, right, and these two matrices we have defined earlier, the matrix of 0 here, matrix of 0, like this. So, this is a 2n by 2n matrix and this is a matrix of size n by n, and this also is a matrix of size n by n. All these are matrices are of size n by n. So, these are the orthogonality properties in terms of the mass normalized, in terms of the normalized eigenvectors. Okay. So, now we are in a position to define model, right. So, let us define model for a multi-degree of freedom system with non-proportional viscous damping. So, it consists of 2n complex conjugate eigenvalues, or maybe I can say that rather it consists of n pairs of complex conjugate eigenvalues and n pairs of complex conjugate eigenvectors, right. So, each pair of complex conjugate eigenvalue and eigenvector together define one real mode of vibration of a multi-degree of freedom system with viscous damping, non-proportional viscous damping. Let us now look at how we can perform the forced, or how we can find out the force vibration response subject of the system to harmonic forces. Okay. So, the equation of motion in the displacement coordinates can be simply written as mx double dot plus C x dot plus k x is equal to, now we have a forcing function f, right, where f is a vector of harmonic forces at frequency omega, and it is equal to amplitude vector f naught e to the power I omega t, right. And if we assume that the displacement response is steady state response is given by x naught e to the power I omega t, right, which is true because the frequency of the motion will be same as the frequency of the harmonic forces, but here the amplitude x naught is something which is unknown, right. So, if we substitute these two equations in this, then we can straight away write down x naught, sorry, let me rewrite, you can write down x naught is equal to k minus omega square m plus I omega c inverse is equal to f naught. So, this is the same equation as we got for the system with proportional viscous damping. So, this equation can be used. So, direct solution of the differential equation leads to the same expression for the solution, and this is nothing but the frequency response function matrix alpha omega. Okay. So, this is the steady state part of the solution. Let us now use now the alternative approach, the modal analysis approach, to find the response. So, let us use modal analysis approach. So, in the modal analysis approach, we will not be able to now use the equations in the displacement coordinates directly, because they cannot be uncoupled or decoupled using the eigenvectors we got, right. The eigenvectors will not be able to decouple the matrices in the displacement coordinates. So, we will therefore again use the state space form of the equations. So, the state space form of the equation we got can be written A z dot plus B z is equal to, now we have the force vector in the state space, right. Let us call it f bar, where f bar is nothing but where f bar is given by vector f and vector of zeros, right. So, this is of order 2n by 1, but this f vector is of order 2n by n by 1, and f is of order n by 1, and this 0 vector is of order n by 1, like this, right. Now, here we perform the modal transformation into state space, and we say that z is equal to, now we are going to use the eigenvectors in state space. So, which are the mass normalized rather the normalized eigenvectors are phi bar, and let us say y bar is the vector of modal coordinates, right. So, they are in state space, phi bar and y bar are the modal are the quantities in state space, and if we substitute this in the equation and then pre-multiply. So, we substitute and pre-multiply by phi bar transpose. So, and then let us write that expression first, phi bar transpose A phi bar y bar dot plus phi bar transpose B phi bar y bar is equal to phi bar transpose f bar. Now, if we invoke the authority properties, this matrix is nothing but unity matrix, right, and this matrix phi bar b phi bar is nothing but matrix of negative of the matrix of eigenvalues, right, minus S bar R. So, therefore, and then if we represent this vector of modal forces in state space by F R bar, right. So, what do we get? We get I y bar dot plus, now we have minus rather, because we have minus sign there. So, minus S R bar y bar is equal to F R bar. So, now these are the equations of motion in modal state space, right. So, these are equations of motion in modal state space, okay, and these are 2n number of decoupled equations. They are all independent equations, 2n number of them, and so each one of them can be solved independently. So, let us pick rth equation, rth modal equation. If we take the rth modal equation, it would be simply y r bar dot minus S R bar into y r bar is equal to F R bar, right. So, this is what we get. So, if you look at F R bar, then this is nothing but the dot product of rth eigenvector and a force vector in modal space, right. And because the force vector is harmonic, we can write this as F bar R transpose F bar naught, which is the amplitude of the force vector in modal space, e to the power I omega t, right. And therefore, this quantity we can simply represent by F R O bar e to the power I omega t, right. So, if we substitute now these quantities, right, this of course also noting that y r bar therefore can also be represented as y r o bar e to the power I omega t, because if the modal force is harmonic, the modal response is also harmonic, would be harmonic. If we substitute these two equations in the modal equation, we get y r o bar as F r o bar divided by omega, okay, I omega rather, I omega minus S r bar, right, because if we substitute y r o bar e to the power I omega t into y r bar dot. So, we will have differentiation which will lead to a term I omega there, okay. So, this is something we get, okay. And now, if we substitute here F r o bar, which is equal to phi bar 1 transpose, sorry, phi bar r transpose F bar o, right, then we get I omega minus S r bar. So, this is nothing but the amplitude of modal response in state space, right. This is the amplitude of modal response in state space. So, by substituting r is equal to 1, 2, 3 up to 2n, we can find the corresponding modal responses. So, let us determine now what is the response in the state space. So, the response in state space can be obtained by substituting the modal response in the modal transformation, and which was phi bar y bar, right. This was the expression, and this expression can be written as summation of phi bar r and y bar r, right, varying from r varying from 1 to 2n, because there are no 2n number of modes, complex modes, right. Let us substitute this into this expression. Let us go to next page, and so we can write down z is equal to r varying from 1 to 2n, and then we have phi bar r, and then in place of yr we will yr bar we would write down phi bar r transpose f bar o divided by I omega minus S r bar, correct. So, that is what we get. So, and we of course can take out the vector f o bar outside, and we can also write this summation from 1 to n and then from n plus 1 to 2n. We can break it into two parts, and we can write this as r is equal to 1 to n with phi bar r, phi bar r transpose divided by I omega minus S bar r, right, plus with r varying from n plus 1 to 2n, and the same thing can be written down phi bar r transpose divided by I omega minus S r bar. And now we note that the second set of n eigenvectors and eigenvalues, they are complex conjugate of the corresponding first quantities in from the first set, and in view of that we can write this expression as phi, this first term remains as it is, phi bar r transpose I omega minus. So, let us represent therefore, this from the eigenvalues from 1 to n, we can simply represent by S r, and then we can represent the next set of n plus 1 next set of n eigenvalues and eigenvectors using the complex conjugate property. So, this would be simply so in fact we can change the limits also. We can simply say that it is from 1 to n, and this is now phi bar r transpose, right, and phi bar r transpose star transpose, and this is nothing but I omega minus S r star, right. And therefore, we can in fact combine these two expressions into a single sum, and we can write this as phi bar r transpose I omega minus S r plus phi bar r star phi bar r star transpose divided by I omega minus S r star. So, this basically gives us the steady state response to the harmonic forces in state space, right. This is nothing but the steady state response in the state space. So, I think one correction I would like to make, I have forgotten to add the vector f naught here. Let us do that. Okay. So, f naught, and this also has f naught. Okay. So, this is the expression. So, if we are interested to know the response only at the displacement coordinates, which means we want to know the displacement part of the response, then we need to simply pick up the first n coordinates from the vector z. That would give us the response in the displacement, that would give us the displacement response, right. So, if you take the first n coordinates from the vector z, we get the displacement at different degrees of freedom, and let us write down that expression now. So, I am directly writing down that expression after substituting the vector f bar o, which is f and vector of zeros, right. If this is substituted, then we can obtain the displacement vector which will be equal to this of course would be x o, right, because it is the amplitude of the displacement, and this would be phi r transpose I omega minus s r plus phi r star phi r star transpose upon I omega minus s r star, right, and this we can also also have the vector now f here, right. So, this is the expression we get for the, and of course not f but f naught, here also will be f naught. So, this is the expression we get for the displacement vector. So, now by adding the complementary part to this, we will obtain the complete solution, right. So, let us now look at what is frequency response function for this system. Let us obtain the frequency response function. So, the frequency response function we can simply obtain by let us say if we are interested to find out the frequency response function alpha j k, right, which is nothing but the response at the jth coordinate due to the force at kth coordinate, and similar to the process we followed in earlier lectures, to find this frequency response function from the steady state response, we define the force vector as being consisting of no forces at all the coordinates except at coordinate k, which is subjected to a harmonic force of unit amplitude. So, this is let us say the kth coordinate, and then if we substitute this in the equation above, and then we extract only the jth response, right, response at only the jth coordinate, then that would be simply x o j, and that would be given by phi j r phi k r upon I omega minus s r plus phi j r transpose star phi k r star divided by I omega minus s r star, right, and this is nothing but alpha j k. So, this is the expression for the frequency response function alpha j k. Okay. Similarly, if we are interested to know the FRF matrix, then the FRF matrix is simply the coefficient of the vector f naught on the right hand side of the above equation, right. and that is simply given by phi r transpose divided by I omega minus SR with R ranging from 1 to n, right, plus phi r into phi r star. So, this is star transpose divided by I omega minus S r star. So, this is nothing but the FRF matrix. So, one difference we see now as compared to the FRF matrix for an undamped system or a system with structural damping or system with proportional viscous damping is that on the right hand side of the FRF matrix now we have n number of 2n number of terms which are appearing, right, because now there are 2n number of complex modes, but in case of the other three systems n modes could define the behavior of the complete system, right, but here there are 2n number of complex modes and hence we are having 2n number of terms on the right hand side. Okay. Of course, they are related by complex conjugate property. So, in this way today we have analyzed the multi-degree of freedom systems with viscous damping, and now I think we can stop here. Thank you.